to the Late Show with the Heinz Brothers. I'm Heinz. Tonight our show is about the physics of superhero movies. Our first guest tonight was able to take time out of his busy lifestyle to come meet with us today. And here he is, our friendly neighborhood Spider-Man. We're glad to have you, Spidey.
And I'm glad to be here.
Please have a seat.
As my uncle once said, with great power comes great responsibility, and it's my responsibility to be here.
Yes, so we have a clip of you following 80 series in Spider-Man 3, which you started in 2007. We would like you to know that that action scene that you were a part of doesn't seem to conform to the laws of physics. Had you been a normal person, you would have been a spider slushie. We have calculations that would let you know what would happen if you were a normal person. Let me remind you of that scene.
We can calculate how much force the ground exerts on Spider-Man when he hits the ground using Newton's second law of motion, which holds that the net force of an object is equal to the mass times acceleration. The forces in the y direction are the normal force, which is upward, and the force of gravity, which is downward. We can set this equal to ma and solve for the normal force.
Here's the free body diagram.
Doing some algebra, we get that the normal force equals m times the quantity of g plus a. A can be rewritten as change in v over change in t. The mass of Spider-Man is 76 kilograms. For g, we will use 9.8 meters per second squared. For v, we will use 53 meters per second, which is the terminal velocity, or the highest velocity that an object can attain in the air, which is about 53 meters per second for a skydiver. For t, we will use 0.01 seconds, since collisions usually take place within 1/100th of a second. Solving for the normal force, we get about 403,544.8 newtons, which is equivalent to 45.36 tons. Plugging this into Newton's second law again and solving for Spider-Man's acceleration when he hits the ground, we get 5,309.8 meters per second squared. He's hitting the ground with an acceleration of about 542 little g's.
Okay, but what are you trying to say?
I'm just trying to say you have an extraordinary skeletal system. You must drink a lot of milk.
Well, my aunt... Oh, I'm sorry. It looks like the vulture's up to no good. I'm gonna have to go.
Wait.
Be sure to watch Spider-Man Homecoming July 7th. With Spider-Man gone, we can welcome the next guest, Batman. Where is he? Hello, Batman. It's good to see you.
I don't shake it.
Okay, please have a seat. So we have a clip of you from 2008's Dark Knight in free fall, saving a girl, and you fall. You land on a car unharmed. Let's see the clip.
Let her go. Very poor choice of words.
To find the force that Rachel and Batman impacted onto car, we must first find acceleration. To find acceleration, we must find change in velocity. To find change in velocity, we must first find final velocity. Use the equation to find final velocity, but we need time first. To find time, we use one of the kinematic equations. We know that initial velocity is 0, and then you just isolate the t. We plug in 110 meters for distance, as that's the building they use for filming. We find time to come out as 4.7 seconds. With this, you can finally find that final velocity was negative 56 meters per second. Now you can plug in negative 56 meters per second minus negative 9.8 meters per second to find change in velocity as negative 46.2 meters per second. Change in time for when they impacted the car was 0.3 seconds. You divide these two numbers to find acceleration, which is 147 meters per second. You can use Newton's second law, force equals mass times acceleration, to find how many newtons this was. You combine Batman and Rachel's mass to get 160 kg, and then you multiply these two values to get 24,000 newtons. Newton's third law would have them dead as the force would be equal onto them.
In another Dark Knight scene, you are on your Batpod against the Joker in the Hit Me scene. Here are the calculations.
Hit me!
The physics in the scene is incorrect as the Joker manages to walk toward Batman in a couple of seconds, which implies that Batman only skid for a couple of meters. We can use the work energy principle to prove this. It states all work done by all forces acting on object equals the change in kinetic energy. This means that the work friction equals the force of static friction, which equals kinetic energy. We can isolate the distance and cancel out the mass. Then we use our assumptions for the given to plug in our numbers, and we determine that the distance is actually 147 meters. It would take Joker about 2 minutes to reach Batman.
How can you explain defying the laws of physics in a movie twice?
Because I'm Batman. I gotta go.
Look, over there. Oh my gosh, what is that?
I think it's